Assalamualaikum and good day everyone. We are from group AS2731B1 and today we will present our topic how cellulose is shaping sustainable packaging. Our team member consists Nurul Hazrani Nazira, Nur Awalun Najah, Fairuz Munirah, Nur Diana Alia and Cik Shafiq Aidil. Let's first understand the global plastic crisis that has become a major environmental challenge worldwide. Petroleum-based plastics are widely used because they are cheap, lightweight, and durable. In fact, around 36% of global plastic production is used for packaging. However, the production and disposal of these plastics contribute significantly to carbon emission and environmental pollution. Another major issue is microplastic contamination. Every year, billions of tons of plastic waste are generated. Improper disposal methods such as landfilling and ocean dumping cause plastics to break down into tiny particles called microplastic. These particles can enter ecosystem, contaminate food chains, and pose risks to both human and animal health. The situation is expected to worsen in the future. If current trends continue, plastic leakage into oceans could increase dramatically by 2040 and reach approximately 12 billion tons by 2050. Therefore, there is an urgent need for sustainable alternatives to conventional plastics. One promising solution is green functional food packaging or GFFP. Now, let's look at cellulose, one of the most important renewable materials for sustainable packaging. Cellulose is the most abundant renewable biopolymer on Earth. It is naturally produced by plants and is available in large quantities. It serves as the primary structural component of plant cell walls, providing strength and rigidity. Besides plants, cellulose can also be found in algae, tunicates, and certain bacteria. An important advantage of cellulose is that it can be obtained from sustainable feedstocks, especially agricultural residue that are often treated as waste. Example includes wheat straw, rice husk, coconut shell, and fruit peels such as orange, mango, and banana peels.
This is the structure of cellulose. Its chemical formula is CHM5 indicating that cellulose is a polymer made of repeating glucose units. The 2D structure show beta-D-glucose molecules linked together by beta-1,2,4 glycosidic bonds. These bonds form long strand chains. The 3D ball and stick model illustrate the spatial arrangement of atoms within the cellulose molecule. The linear structure allows many hydrogen bonds to form between neighboring chains, giving cellulose its high strength and rigidity. Now, let's look at the properties of the cellulose. For physical properties, cellulose is a white fibrous polysaccharide that is insoluble in water due to strong hydrogen bonding between cellulose chains. It has high tensile strength, making it an important structural material in a plant. It is also biodegradable, renewable, and relatively stable under heat. Next are chemical properties. Cellulose is made up of beta-D-glucose molecule connected by beta-1,2,4 glycosidic bonds. These bonds form long straight chain that create strong hydrogen bonds with neighboring chain. Cellulose can be broken down into glucose through hydrolysis and can also be chemically modified to produce useful derivatives such as cellulose acetate. Moving on to its biological role, cellulose is the main component of plant cell wall. It provides structural support, maintains cell shape, and helps plants remain upright. In fact, cellulose is the most abundant organic polymer found on Earth.
Cellulose used in sustainable packaging can be obtained from plants or produced by bacteria through microbial fermentation. To improve its properties for packaging application, cellulose is often converted into cellulose nanocrystal or CNCs. This is achieved through acid hydrolysis, where mineral acids remove the amorphous regions of cellulose while preserving the crystalline regions. The resulting CNCs possess high strength and excellent barrier properties. The cellulose fibers are treated with acid. The acids break down the weaker amorphous regions while leaving behind the stronger crystalline regions. These remaining crystals are called cellulose nanocrystals or CNCs. Next, the CNCs are dispersed in a solvent and cast into a film. As the solvent evaporates, hydrogen bonds form between cellulose chains, creating a strong three-dimensional network. This process produces a thin, biodegradable biodegradable packaging film that offers an environmentally friendly alternative to conventional plastic packaging.
Hey everyone, let's check out how we extract cellulose nanocrystals, these tiny, super strong structures hiding inside everyday plants.
So, how exactly do we harvest nature's strongest building blocks? Well, we use chemistry to strip away the weak stuff.
It all starts with raw plant cellulose fibers. You know, those tough, messy threads? That's our literal starting point.
We use a quick three-step process here. First up, acid treatment, then structural breakdown, and finally, crystal extraction. Step 1 is wild. We literally dunk those raw, tangled plant fibers right into a highly reactive acid bath. The acid completely destroys the weaker, messy parts of the plant, basically melting away those chaotic tangles. But get this, the tightly packed crystalline regions actually survive. Nature's most resilient architecture gets left totally intact. We call these survivors cellulose nanocrystals. Mix them into a liquid, and their chains form super strong hydrogen bonds. As that solvent evaporates, a 3D network creates a thin, biodegradable film. Boom! Sustainable packaging. Could this replace plastic?
Next, we move to the application. Cellulose has many applications in sustainable packaging, particularly in food packaging. It is commonly used to produce edible films and coating for fruits, vegetables, seafood, and meat. These films help extend shelf life, reduce food spoilage, and minimize the use of conventional plastic packaging. In addition, cellulose is widely used in biodegradable packaging as an environmentally friendly alternative to petroleum-based plastic. Unlike conventional plastic, cellulose-based material can naturally decompose and do not contribute to long-term microplastic pollution. Another important application is intelligent or smart packaging. Cellulose-based packaging can be integrated with sensors or indicators that monitor food freshness and detect spoilage, providing real-time information about product quality and safety. Furthermore, cellulose nanocrystal and nanofibers can be incorporated into bioplastic to improve their strength, flexibility, and barrier properties. This result is lightweight, durable, and sustainable packaging materials that can be reduced dependence on fossil fuel-based plastic. We move to the health implication. Cellulose-based packaging has several important health implications. First, cellulose is non-toxic, biocompatible, and generally recognized as safe, making it suitable for food contact application. In addition, cellulose is biodegradable and breaks down into non-toxic byproducts, reducing concerns associated with microplastic exposure. However, some advanced cellulose-based packaging material contain nanomaterial such as cellulose nanocrystal and zinc oxide nanoparticle. Therefore, their potential migration into food must be monitored to address nanotoxicity concerns and ensure consumer safety.
Next, I will discuss some of the latest research and innovations involving cellulose. First, researchers are developing aminate cellulose nanocrystals as smart drug delivery system. These cellulose-based nanoparticles can carry compounds such as curcumin, which is an antioxidant found in turmeric. When they reach inflamed tissue or tumor sites that have a more acidic environment than healthy tissues, they release the drug in a controlled manner. Second, researchers have developed intelligent packaging films by combining polydiacetylene with cellulose-based material. These films can detect ammonia gas produced when seafood begin to spoil. As ammonia level increase, the film change color from blue to red, providing a simple visual indicator of food freshness and helping to improve food safety. Finally, researchers are creating biodegradable plastic by blending cellulose with biodegradable polyester such as PLA and PBAT. PLA is derived from renewable resources like cornstarch and sugarcane, while PBAT is flexible and compostable polyester. The addition of cellulose improves the strength and durability of these materials, making them promising alternative to conventional plastics. Current research demonstrates that cellulose is far more than a traditional paper-making material. Through innovation in drug delivery systems, intelligent food packaging, and biodegradable plastics, cellulose is emerging as a key material for sustainable technologies that improve human health, food safety, and environmental protection. Cellulose is the backbone of a sustainable circular economy. This bio-friendly material can degrade in soil within just 7 days without polluting the environment. By moving beyond plastic, we are building a future where packaging is as smart and green as nature itself. These are the references used for this presentation. The information was gathered from recent and reliable scientific journals on cellulose application in sustainability. That's all from our group presentation. Thank you for your attention and have a nice day, everyone.